Good day, students. My name is Ixindio, one of the chemistry teachers in Jena School, a school located at Ayobo, Lagos. Today, we are going to look at mass and volume, a topic for an SS2 class. Now, some of you might even ask the question that mass versus volume, are they fighting a wrestling contest? Or is it a UFC fight? But in chemistry, we tend to look at some of these things, the quantities. Now, everything we have ever known or experienced is matter. And remember what we said, that if you look at matter, which you've started learning from primary school, you will agree with me that the simplest of all definition of matter is that matter is anything that has weight and occupies space. Then this will be broken down into the three states of matter as number one, solid, number two, liquid, and the third one, gas. Then in each case, we all know what is likely to happen in each case, what we have there. So if the particles are in the solid state, they are fixed in the containers in such a way that they will not have space to move about. So we say they are arranged in a lattice, L-A-T-T-I-C-E. Then, and all matter has mass. So anything, matter has mass, the weight. So you could have this chemistry table here, you could have the stools you have around here, they are all fine, they all have their mass. Now, the ground we walk on is matter. The air you breathe is matter. And there's even matter in space. Now, let's look at matter itself. Matter is the amount of stuff. This stuff here, that's the amount of quantity inside an object. The more the quantity, then the more there is, that's the matter that is inside that particular substance. Matter is made up of atoms and molecules, and the more of them we have, the more the mass of an object is. So from here we have atom, that's the smallest indivisible particle of an element. So if we are taking a case study of two elements, or let me just take the simplest of them all, hydrogen as the number one element on the periodic table and having the symbol capital letter H. So if I'm going to write atomic hydrogen, it becomes capital letter H. So if we are taking the hydrogen in molecule form, it becomes capital letter H2. So it becomes a gas at this level. That's why we're looking at this and this. And the more of them we have, the more the mass of an object is. We measure mass in units like kilograms, ounce, and pounds in science. That's why most times when you watch wrestling matches, they will tell you that so-so person, wrestler, Roman Reigns weighs this, a boxer weighs this before fight, and that. So in kilograms, you could also measure your bags of rice, your 10 kg semoviters, and the rest of them. We prefer kilograms. Now look at it, you said, so there are other ways in which you can measure your mass. You can measure it in kilograms, you can also measure in grams, but the accepted one internationally you have. So what I'm trying to say now is that I cannot say, Mr. Dixon, and probably let's take for example, I step on the weight balance and my weight is 50. Somebody will ask me, 50 what? Could it be 50 naira? Is that your weight? Could your weight be 50 kobo? But by the time I indicate the right unit, it becomes 50 kilograms. So immediately the person sees, okay, that's Mr. Dixon's weight. He weighs 50 kg. So you don't need to go about perambulating or asking, what does it mean by that? Then which are the SI, that is the standard international unit. The standard unit in which you can measure all these things. Unit of mass. Your bedroom scale is calibrated. When we use the word calibrated here, it means it is marked off. Calibration. So for every equipment in science, they are all calibrated. Your glassware you use in chemistry are calibrated. So the calibration could be from 0 to 50 cm. I hope I'm communicating. That's what you have. They are marked off to tell you your mass. So once you step on that particular balance, then you will stand right, because tilting your body could reduce whatever is coming, or it might be altering it. There's some other person will look at it to read off where the arrow is pointing to tell you, hey, you weigh 20 kg or thereabout. But it only works properly on Earth. Now remember, we're not talking about space here, because when you move to space, you'll be experiencing weightlessness. So on Earth here, you have the gravitational pull on the Earth's body, which is in line with Newton's law of gravity, that anything that goes up must come down. So if I throw my ruler, if I throw this up, it will definitely drop. So there is no how, nothing will be wedging it. But in space, once you throw it, you will be the one, the thing will go off itself and it will be floating. That's what I'm trying to say. So, but it only works properly on Earth. Then, if you took it to the moon, now that's a bit specific now, but if you took it to the moon, the weight, if you took it to the moon, the weight on the scale will change. For example, if I have 50 kg here and we get to moon, it can be the same weight. But of course, your mass would not. So, look at these two things here. If you took it to the moon, the weight on the scale. So if they say the weight, then that means there's a difference between weight and mass. That's what I'm trying to tell you. So here that, from this place, understand what is going on here. That, well, please go. Alright. Then if you took it to the moon, the weight on the scale will change, but of course your mass will not. So your mass still remains the same. That is the quantity of matter that is inside the body. That is what they are trying to say. Now let's look at volume here. Volume is how much space something takes up. So for example, I was telling somebody the other day, I said, okay, get 2 containers. Drop me 2 containers like I have this. If you look at your Pepsi container, you will always see where it is calibrated. They will tell you this is maybe 60 cl. You have it here, 60 cl. So what they mean is that this container can only contain a liquid that is not more than 60. So anything you are bringing inside here that is 61 cl will not go in here. So it will spill. That means I need to get a bigger container that is about, let's say, a 70 cl that will pave roof for that 1 cl that will come into this particular container. That's what we're trying to say here. Now, that is how much space something takes up. So the standard unit of volume is meters cube. Meters cube or cubic meters. Most cases they will always tell you, you first of all pronounce the power on top of it before bringing the units you have in question, that is in cubic meters. The classic question people ask to show the difference between mass and volume is, that's a classic question. What has the greatest mass? A pound of feathers or a pound of nail? That's the question. Look at it. They said, what has a pound of feathers or a pound of nails? Well, it's a pound of each. So they both have the same mass. This was demonstrated by Galileo Galilei, one of the scientists that stood atop a particular place. And he dropped a feather and another object. And the question now is that it's an experiment you can carry out. Maybe those of you that are living on 2-story building or in your flat, you just come to the balcony and you get a very light object and another one and you drop them and you watch them. Then you'll be able to say which of them will drop. It's like picking a feather and a cotton wool. Cut one piece of cotton wool and the feather and I release them at the same time. If you have a stopwatch, you could also say which of them, or you have your brother standing downstairs, he'll be able to tell you what to do. Well, it's a pound of each. They both have the same mass. Now look at it here. It's just that a pound of feathers will take up a huge amount of space. A pound of feathers, it has a greater volume. That's the question they are trying to ask you. Now, formulas for mass and volume. Now, remember, one thing that makes chemistry very interesting is the ability of the students to be able to memorize formulas, interpret formulas, and know the right formula to use in answering the question. So when the question is given to you in chemistry or in physics or anyone, you should be able to bring out the parameters in the question. Bringing out the parameters will give you a hint on this is what I'm supposed to do, and so I won't be beating around the bush. Now let's look at it. Formulas. Mind you, if you change this S to E, it becomes formulae. So if it's formulae, it is also an accepted version of the plural form of removing this one. So if I remove this S here now, it becomes formula, singular, and the auxiliary verb that will be going before it becomes an is. So formulas are about relationships between numbers, like we said. relationship between numbers, which we have been looking at. Mass and volume relates to each other through a concept called density. That is mass per unit volume of a substance. Look at it. Concept called density. Your rho you have in there. You said density. Let's look at density. Density is how tightly packed the atoms and molecules in a substance are. Measured in kilograms per meter cube. Now, if you have a lot of mass in a small area, like you have a lot of mass in a small area with high density, you have little mass spread over a large area. That's low density. Now, the formula that relates density, mass, and volume, there are three parameters here: mass, volume, and density. Look at it here. This relationship: 1, 2, 3. This is density, this is mass, and this is volume. So this is the relationship that. So here, all we just need to pick the SI unit of mass here, which is what? Kilograms, and we pick the SI unit of volume here, which gives us what? Meter cube or cm, depending on the question asked. So if I have here, this will give me kilograms per cubic meters. That is the density I have here. It will also be pascals, like in the case might also be. Now, from this place now, we have here, m represents the mass of a substance. Remember the relationship P is equal to m over V. Represent the mass of the substance, the mass of an object or material. V represents the volume, and they call it P. Look at the key word here. They use an adverb. Look at it here. It's an adverb they are trying to explain what it is calling. It's not written as, look at it, it's not written as a normal letter P. Call it P, which is the Greek letter rho. It's the Greek letter rho. So it is not the usual P you write, but the way it comes is calling letter rho. Now, representing density. So rho is equal to mass per unit volume of the substance. That's m over v. There are also many formulas for volume, depending on the shape of an object. So the way to calculate the volume of the substance is different than how you calculate the volume of a cube or cuboid. That's what we're trying to say. So you are looking at a cube now. These are solid materials. I'm looking at, let's say, your Maggi cube. Let's say your normal century sugar cube. Then you pick a cube, a matchbox. A matchbox is a cuboid. And I ask you now, hey, please, how do you calculate the volume of this cube? And how do you calculate the volume of the cuboid? You just tell me that the volume of the cuboid, because a cuboid is a 3D shape. A cube is also a 3D shape. So you tell me volume of a cuboid is length multiplied by the breadth multiplied by the height cubic units. So the unit could be in centimeters, it becomes cubic centimeters. Then if I'm looking at the cube on its own, the volume will give me L cube unit cube. That is each side. So remember that all the sides are equal. If it is 5 centimeters, I'll have 5 times 5 times 5 in that order. Look at it here. We talked about it. 3D shape and their formula. Look at it. Cube or cuboid, which I've just realized. That's length times the width times the height, which is the same thing as the breadth you have here. It's like looking at this interactive board now. This is the length of the interactive board, and this is the width. That is from here to here, which is the same thing as from here to here, which is the breadth. So the width and the breadth are the same thing, times the height. So if it is a cuboid, we all know how a matchstick looks like. Then we could have a projection coming out from this point, and we are taking the height. So our height will now be from here to here if it's a matchbox. Then we have a sphere. A sphere is 1/6 pi d cube, where d is the diameter. So if it's a sphere, which you know, all we need to do is that in removing this one, if you are converting it to radius, you just divide your radius by 2, and you have that. Now, prism here, we have our prism, and we are being specific. What's the nature of the prism? Is it a triangular prism? The base is triangular, or is it a rectangular prism? Remember that prisms are named according to their bases. So that means if it's the base of the prism, if it's in triangular form, you call it a triangular prism. If it takes the shape of a rectangle, you call it a rectangular prism. Are you getting now? Then cylinder as well. So you have here that area multiply by length. So area of the end you have from that side, multiply by the length of the prism. Alright? So let's see some unit conversion. See, one thing that is so interesting about science is that for you to enjoy sciences, you must be able to convert from one unit to another unit. That's the beauty of science. So if you're able to convert from one unit to another, then you are going to flow very well in your sciences. Unit conversion. We have already talked about the standard unit of density, kilograms per meter cube, that's km per meter cube. Mass, that is the kilograms, mass is measured in kilograms, and volume in meter cube. Remember, whatever we are measuring is always in meter cube. Now, you have, when we're in primary school, the normal chanting, your teachers will tell you, okay, recite your metric table conversion. Then we all agree, they will say 10 centimeters, make all this, 100 cl, make this, and the rest of it. So you should be able to recall all that. But sometimes people use standard or non-scientific units. For example, if someone uses a mass in grams, look at it here. He's using mass in grams, and a volume in centimeters. Look at it. Mass. Remember we talked about standard unit of mass in kg. Now he's using the mass in grams. Now he's not using the kilogram, and he's using his volume in centimeter cube. That's cm cube. He's not using it in m cube here. Now the density will come out in grams per cubic centimeters. Do you get it now? So if the dimensions are given in meters, my density rho will come out in that slash cubic cube or dash slash cubic meters, depending on the unit. So if it's given as 10 meters, the answer is going to come out in meter form. But sometimes in sciences, they will confuse you. What they want to do is they want to test your intelligence quotient. They will give you the length in centimeters, give you the breadth in meters, and they will say, leaving your answer in cm. So immediately you see leaving your answer in centimeters, the one in centimeters you leave, then you convert the one in meters to centimeters. And recalling that 100 centimeters will make 1 meter, which you know. Then, but once your unit conversion is wrong, then everything you are doing will blow up into thin air like smoke, and it will vanish. You'll be looking at it while the thing will vanish. Now let's look at what we have here. It said in those situations, it can be helpful to convert between units. You might need to multiply or divide. You can see it, like I used to tell people. I say, if for example you are told that 100 centimeters will make 1 meter, that is, I have 100 centimeters going to give me 1 meter. Then the question I now ask myself is that in science, I don't need to cram anything. If you now bring in a simple rule of big to small, 100 centimeters will make 1 meter, small to big. So anytime I'm changing from big to small, that is meters to centimeters, I will multiply. Anytime I'm changing from small to big, I will do what? I will divide. So depending on what the case is. So the units, the figure involved could be 1,000, it could be 100, it could be 10. So the most important thing is that you must not gamble. In science, you don't gamble. So where you need to multiply, those are the 2 basic rules. Let's take that again. Let's look at it so that we can understand what we have here. To convert between units, you might need to multiply. Look at it. Or divide. So if I make the mistake of dividing when I'm supposed to multiply, that means all the while I've been doing since morning, it just blew up. Here is some information that you might need. Let's use the information in bullet forms we have there. That's what I was trying to say. There are 1,000 grams in 1 kilogram, meaning that 1,000 grams will make 1 kilogram. You say 1,000 grams will make 1 kilogram. So if in the exam you are working with grams and kilograms, and the examiner now said, leaving your answer in grams. And when you go to this place, instead of using the normal 1,000 grams, then you now said, 100 grams is equal to, God, that's the end of it. That is just it. So from here, if you remove this 0, it alters everything completely. So here we should have it at the back of our mind. We shouldn't eat anything with it. Have it, put it in your medulla, and lock it up there. That 1,000 grams will make a kilogram. Now, look at the second point you have here. There are 100 centimeters, like I rightly said, in a meter. That is 100 centimeters will make 1 meter. So I can't say 10 centimeters will make 1 meter. Somebody will just look at you. What did you just say? So you need to be very, very conversant with these figures So immediately, like here now, I can say 1,000. So it's like your normal ruler you have in your math set. If you look at the normal ruler you have in your math set, you will agree with me that the units are always calibrated in centimeters and in millimeters, if you look at it very well. Okay, so let's look at what we have here. There are roughly 2.2 pounds in a kilogram, or 0.45 kilograms in a pound. So this is also conversion that you have to adhere strictly to. There are 16 ounces in a pound. There is 0.0823 cubic meters in a cube, in a cubic foot, or 5.31 cubic feet in a cubic meter. So whoever is into construction and a whole lot must be able to know this, and as a scientist. There are 1,000 meters in a cubic liter, and there are million cubic centimeters, 1 million cubic centimeters in a cubic meter. So when you are converting, you'll be taking into cognizance the cube you have in that particular place. I hope I'm communicating. Alright, so there are 1,000 meters in a cubic meter, there are a million cubic centimeters in a cubic meter, and so on and so forth. So class, what we are trying to say here is that we must be very conversant with our metric table conversion so that we're able to get the best out of it. So metric table conversion makes you a better scientist, makes you a better solver, and makes you, in those days in school, some students will solve some question and you call them solution dissolvers or solvers. So I want to believe that while you guys are on lockdown, you'll be able to make use of your time wisely, study very hard, and pray that God will whisk the COVID-19 away so that we go back to our normal school studies for a better classroom teacher relationship. Thank you very much and have a lovely day.